Welcome to this explainer. Today, we're jumping right in to demystify exactly how your computer manages data, focusing entirely on the fundamental differences between primary and secondary storage systems. It is an absolutely fascinating, high-speed dance happening right under your fingertips.
So, let's kick things off with a simple but kind of profound question. If storage is just storage, why does your device desperately need two completely different types of memory just to function? I mean, why not just build a computer with one massive drive that handles absolutely everything?
To answer that, here is a roadmap for today. We'll cover the desk and bookshelf analogy, volatile versus non-volatile memory, the memory hierarchy pyramid, how data actually moves around, methods of file access, and finally, the ultimate system trade-offs. Part 1. The desk and the bookshelf, a relatable metaphor. Let's start with a brilliant real-life analogy that perfectly captures the basic division of labor inside your machine.
Think of primary storage as your actual working desk. It provides a temporary, relatively small, but incredibly fast workspace for whatever active tasks you're working on right now. Secondary storage, well, that is the massive bookshelf sitting over in the corner of the room. It acts as a permanent, large, and somewhat slower long-term vault for all your files and programs. You definitely wouldn't try to store every single book you own on your small desk, right? And you certainly wouldn't try to actively read and write a document while it's still sitting closed on the bookshelf.
Moving to part 2, volatile versus non-volatile memory, the power factor. What actually happens to your desk and your bookshelf when you completely pull the plug on your computer? The absolute crucial point here comes down to volatility. You see, primary memory, like your RAM, is volatile. That means it completely wipes itself clean the literal second it loses power. It's incredibly fast for sure, but purely temporary. Secondary memory, like your hard disk drives or solid-state drives, is non-volatile. It safely retains your data even when the system is totally shut down. Also, notice the CPU access here. Primary memory is directly accessible by the processor, but secondary memory is not. Section 3. The memory hierarchy pyramid. Let's visualize this architecture and see how it physically builds out.
When we map this architecture out as a rigid, multi-tiered pyramid structure, things get really interesting. As we travel from the bottom base, where we have things like magnetic tapes and optical disks, all the way up to the CPU registers at the very top, a few distinct things happen. Access speed increases dramatically, and the cost per bit absolutely skyrockets. Because the top layers are just so expensive to manufacture, the overall storage capacity drastically shrinks the higher up the pyramid you go.
So, breaking down the top of that pyramid, levels 0 through 2, this is your primary memory. We're talking highly advanced, expensive semiconductor tech. This includes CPU registers, extremely fast SRAM used for cache, and DRAM used for your main memory. The vital takeaway here is that this layer gives the processor an immediate, direct connection to your active data. It's the ultimate working desk.
Now conversely, the base of the pyramid is your secondary mass storage. This is where you hold hundreds of gigabytes, or even terabytes, of persistent data. It includes magnetic hard drives, flash-based solid-state drives, and optical disks. But remember that crucial limitation? The processor actually cannot interact with this massive bookshelf directly. Section 4. How data moves around. The journey of a file. Since the CPU can't directly read from the bookshelf at the bottom of the pyramid, how does a file actually get to the desk to be worked on?
Okay, let's dive into this workflow. It's an elegant 4-step journey. First, your data is just resting safely in secondary storage. When you double-click to open a file, your operating system uses a slick technique called paging. It temporarily loads blocks of that data from your slow secondary storage right into the fast primary RAM. Step 3, the CPU actually processes the data directly from the RAM. And finally, when you hit save, that newly processed result is written right back down to the permanent secondary storage. To optimize this whole flow and keep the CPU fed, systems rely on a brilliant concept called the locality of reference. Basically, your system acts like a hyper-efficient assistant. It predicts what data you'll need next based on what you just used, or what data is physically stored nearby. It then proactively buffers that data into ultra-fast cache memory, ensuring the CPU is never kept waiting around for the slower RAM or secondary drives. Section 5. Methods of file access. Locating the data. When we are dealing with massive secondary storage drives containing literally millions of files, how does the OS physically locate and retrieve the specific block of data you want?
You generally have two foundational methods for this: Sequential access reads records strictly in order, one by one. It's very much like fast-forwarding a cassette tape to find a specific song. It's simple, sure, but it is incredibly slow for searching. Direct access, on the other hand, allows the system to jump directly to a specific block's address for random access, making it significantly faster.
For really large files, modern systems often combine these strategies into the index sequential method. Think of it exactly like the index at the back of a heavy textbook. The system constructs an index containing pointers to various data blocks, which allows the operating system to perform extremely fast direct lookups before it starts reading the actual data sequentially.
Then there's a highly advanced approach called Content Addressable Access, or CAA. Instead of searching for where data physically lives on the disk, CAA uses a mathematical hash function to locate data based on what it actually contains. It generates a unique key for the content itself. Now, while this requires a bit of overhead just to calculate that hash, it is profoundly efficient for managing huge databases.
Now imagine transferring giant video files right from your hard drive into your RAM. To keep the CPU from getting completely bogged down managing that heavy traffic, hardware engineers came up with Direct Memory Access, or DMA. DMA basically acts as a special controller that lets secondary storage write data directly into primary memory via the system buses, totally bypassing the CPU and keeping your system snappy and responsive.
Which brings us to part 6, the ultimate system trade-offs. Let's see how all this builds into the ultimate balancing act of modern computer architecture.
Because at the end of the day, computing relies completely on a delicate triad of trade-offs. Look, if you want lightning-fast CPU speeds, you absolutely need primary memory, but you sacrifice capacity. If you want mass retention, you need secondary memory, but you sacrifice speed. And tying the whole shebang together is economic feasibility. We have to balance both primary and secondary systems to create a machine that is fast, spacious, and actually affordable to build. Ultimately, one provides your active, high-speed temporary workspace, and the other acts as your enormous, permanent vault. They aren't interchangeable, but they are perfectly complementary. They orchestrate a complex, high-speed dance every single time you turn on your machine, launch an application, or save a file. Which leaves us with this final, kind of provocative thought to wrap up the explainer. As modern flash technology, like the SSDs and the laptops we use every day, continues to blur these lines, getting exponentially faster, highly durable, and ever cheaper, will the computers of tomorrow eventually merge the desk and the bookshelf into a single universal storage system? It's a fascinating engineering frontier. Thanks for hanging out with me for this explainer. I hope you walk away with a crystal clear understanding of the memory inside your machine.